So this talk is Recursive Query Throwdown in MySQL 8. My name is Bill Karwin. I am a software developer and have been using MySQL for a long time, since 2000 approximately. I've also written a book called SQL Anti-Patterns, and that came out a few years back, but it's proved to be pretty popular. I had fun writing it and got a lot of good feedback. And as of this week, I'm an Oracle ACE director. Thank you very much. Yay, me. So this topic is about how to query a tree. Tree structured data is something that we face a lot in our applications. So some examples of types of tree structured data could be organizational charts. So I have an illustration of one here on the slide. Categories and subcategories. For example, if you've got a product catalog and you want to have shoes, and then underneath that is athletic shoes, and underneath that is red athletic shoes, whatever. You can have categories within categories and so on. Parts explosion, which is a term often applied to inventories and assemblies of things. I had to do a hierarchical data set for a lab that wanted to reserve servers and equipment. So they said you have a server, and inside the server is a memory card, and associated with the server is a disk shelf, and within the disk shelf are individual disks. So this goes deeper and deeper and deeper as you add parts, and you have to be able to refer to that whole group in aggregate in some way and preserve it and copy it and things like that. So using hierarchies is a useful tool for representing that kind of data. And the last one is threaded discussion groups, often on chat rooms or forums or social media. Hierarchies come into play when you have nested discussions where people reply to each other, and it can have various levels of indentation. We've seen things like that all the way back to Slashdot had a large hierarchy. And Slashdot was interesting because it was open source, and I looked at how they implemented theirs, and they had references from replies back to the message that it replied to, but also every reply made reference to the root node of every conversation, so you could grab everything that made reference to a given conversation as a group. So they sort of had a hybrid approach. So here's an example of a threaded comment set. Maybe this would be a conversation you'd see in a discussion between engineers on a bug database. Have you tried this troubleshooting? We need to put in a valid input check. Yes, that's a bug. So each of these nodes in this tree represents some relationship between the comments replying to the preceding comment, and therefore it represents some continuity of the conversation. And conversations can branch and split and then make reference to earlier comments. So we have some capability of adding in more replies that are replies to older comments. Therefore, we need a tree rather than just a list. A traditional way of representing this in a database could just be to have a table where each respective comment in the discussion thread makes reference to the one it immediately replies to, even though it's out of chronological sequence. So in this case, we have the second comment replies to its parent. We refer to the parent as the one that it's referencing, and the parent is the one up here. So what's the cause of this bug? I think it's a null pointer. There's an obvious reply relationship there. This is very easy to represent in the database, and it's nice in a relational sense because there's one source of authority for which the parent is of any given comment. There's no ambiguity, and there's no way for data anomalies to occur. The relationship is stored in exactly one place. The downside, if you've ever worked in situations like this, is if you need to query the entire tree to display on some web page or some report, you have a task ahead of you that's rather difficult, because how deep can the conversation go? Well, it could go arbitrarily deep. But SQL in its traditional form doesn't support arbitrary depth of joining relationships very well. You can say, well, we can support up to 10 levels deep in this conversation to try to join the replies back to their parent again and again and again. But what if we have a discussion group that goes 11 or 12 levels deep? We don't have the capability of dynamically adding more joins onto the end of a fixed query. We'd have to modify our application code in order to do that. Well, you could go to 20 or 30 or so on, but eventually you get to some sort of fixed limit. So in MySQL, they had this difficulty for a long, long time. So we have a number of workarounds that we had to do. You have a comment? Okay. Workarounds for MySQL that we had to cope with for many years because of the lack of native recursive queries included various creative ways of storing the threads and the relationships between those referencing children and parent relationships to support our ability to query the whole tree at one time when we needed to. And they come by a few different names: path enumeration, nested sets, closure table. Let me give you some examples of these. Path enumeration would look a little bit different. Instead of just having the single reference from a child to its immediate parent, it would have what I would call breadcrumbs, which is a list represented in a string of all the ancestors all the way up to the top of the tree. So in that way, you can make reference to the depth that each node is at in the tree, and you can also use that string to look up the whole sequence of ancestors: parent, grandparent, great-grandparent, and so on. And as long as you can have a long string that supports all of the length of the longest depth of your tree, then that works out well. Trying to do a couple of example queries for something like this, you can use pattern matching. So you can look for to find my ancestors, I can look for the string of breadcrumbs like my own node's path with a wildcard at the end. And likewise, in the reverse operation, I can find the descendants of a given comment in my tree doing a reverse type of pattern matching. And it works out. It's not speedy, although it is a fixed string on the left side of the pattern, so it can use an index. So you can use a single query to get the whole tree when you need to, either the tree above you or the tree below you of a given node. And in that way, that's kind of a pro. However, trying to move a node or insert a node into the tree gets to be fairly complex because you have to modify other paths within the rest of the tree. And we have the bad practice of storing lists of numbers in a single atomic string within the database, and you have all sorts of problems with data integrity there. What if somebody puts in a number in the list that doesn't actually exist in your tree? How long of a list do you need to store? There's a lot of downsides to that. Another solution that was common, in fact, there was an article on MySQL.com for many years about managing hierarchical data sets by Mike Hillier. It's now moved to his personal blog. And it was a creative solution that actually dates back to 1992, where they enumerate all the nodes in the tree using left and right numbers. And it was easier to explain instead of in text. I'll show you the picture. In this case, we have all the nodes in the tree represented like we had before, but each node in the tree has a left number and a right number. And the easy way to look at this is it's a depth first search traversal of the tree. You would just go down the left side of the tree and come back up each branch and keep on going and traverse each branch as you go, and then come back up the right side of the tree and number the numbers in sequence as you are going along there. And that's the organization for those numbers. And it works out. You can actually do interesting queries against this. The data looks like this. Those numbers that are in these new columns, they are not references to the primary key IDs of the nodes. They're just arbitrary sequential numbers. And they go from 1 to essentially 2 times the number of nodes in your tree. And there are ways of querying this, so you can get the same types of queries that we did before to get the subtree or the ancestors whenever you need to, using between predicates. It's like everything below me in the tree has got to have numbers that are greater than my right number and less than my left number. And when you can rely on that, now you can query a subtree. And if you want to get the nodes above you, ancestors in the tree, it's the opposite. They're always going to have numbers that are less than my left number and greater than my right number. Very clever, but not very maintainable. It's rather difficult and complex to try to add a new node into the tree because you now have to renumber a whole bunch of the other nodes and shift them over a little bit in order to make space. I had a friend suggest to me, use floats instead of integers. I was like, well, that gets into even more trouble. So it's a bit of a hassle to do this. And again, these have the potential for data anomalies because they're not foreign keys, they have no referential integrity, and so it's very easy to get out of sync. If you make a mistake in any of those numbers and misnumber it, your whole tree is kind of broken as a result. And the third example is what I have termed closure table, or more properly, I've heard people call this transitive closure relation, which is a way of storing every path through the tree. And I developed this around 2002 myself. I don't know if anybody has done it prior to that. But the idea is you create an additional table in your database, not the one that you're storing your tree nodes in, but a second table in which you store every single path that goes through the table. For the references immediate children, but also paths of length 2, paths of length 3, and etc. Even paths of length 0, where a node refers to itself. And I'll illustrate this. If you've got all your nodes in your tree, and you can imagine how do any of them connect, even indirectly, that forms a path. Some paths are longer than others, so you can actually store every single one of those in your closure table. And if you notice that there's also the little curlicue ones like this one that indicate a node referring to itself. And there's good reasons for doing that when you want to do certain types of operations and searches. What this looks like in the data is that your node data that has the comments in your discussion list, they don't have any other attributes, they just have their primary key. But then your second table over on the side here has every path through the tree. So here's ancestor, descendant, and length. First row says 1, 1, 0, which means a path that starts at node 1, ends at node 1, and has a length of 0. That's the self-referential loop. And then the next one is starts at ancestor 1, goes to descendant number 2, path length 1. So it's just a short hop from the first comment to its immediate child. And then there'd be all the other paths in there. And you can do fairly simple queries for this. For example, if I want to know all the ancestors of comment number 7, I can say every path that terminates at comment 7, then I want to see all the paths that end there. So I'll look back here. Comment 7 is down here, so it's got a path coming from 6, a path coming from 4, and a path coming from 1, as well as its own self-referential path coming from itself. So every arrow that terminates at 7 indicates a linkage with one of its ancestors, because only the ancestors have a path to it. And therefore, you can get a query of all the ancestors that go up the tree. And likewise, you can get subtrees with this technique. You can say, starting at node 4, if I look at all the paths that start there, have the origin point and in node 4, and terminate anywhere below it in the tree, then that is definitely all the paths that start there and go down into the tree below it. So let's take a look at that. If I have node number 4 and I follow all the arrows that exit from 4 that have the ancestor listed as 4, and they connect here to 5, there's one that connects to 6, and there's this leap down here to 7, as well as the reflexive one. So you can get all the paths out of 4 that terminate at anywhere below it, and therefore that's a subtree. So those are just some examples. The closure table has one example, one advantage that the others don't, is that it actually has referential integrity. Those ancestor and descendant numbers are actual foreign keys that can be applied with referential integrity to the other nodes in the tree. However, an extra table is required. It's denormalized in the sense that the hierarchy is stored redundantly on many rows, and if you make a mistake as you insert the data, your tree is kind of garbage at that point. It's also kind of confusing. I've found a lot of people ask me questions about how to use this. They say, I have this type of query and I want this kind of result. How do I do it? Because sometimes it requires several joins in order to get the result that you want. And a lot of developers aren't really comfortable with doing complex joins. So there's got to be a better way. And that's what the point of this talk is. I'm trying to give you some historical context of all the things that we had to do as workarounds before. So what do we do today? Well, Ansi SQL, since SQL 99 in 1999, defined syntax for doing this, but it took a while for a lot of the vendors to catch up, implementations of SQL. And I actually researched and found which databases actually supported the recursive query syntax and when they added it and in what version. So, and if you're curious, you can get my slides and follow all those hyperlinks to see the documentation where they introduced those features. I blogged about this on the Percona blog a few years ago to collect all this data, and found that MySQL was the only vendor of SQL database at that time in 2014 who had not implemented recursive query syntax in the Ansi standard way. I guess it shared that distinction with Informix, but Informix is kind of an old school database as well. So what does this syntax look like? It uses the common table expression syntax that begins with a with keyword, and you can define what I sometimes call an inline view. You can define a query that then can be used in your real query. And the syntax begins to look like a view definition where you give the column names that you want to include in that view, and you say as, which also looks like a create view statement. It has the as and then a following with a query, and you can put any select query that you want into this parenthesized expression, and then following the parenthesized expression, you now have a temporary view which can then be referenced in your subsequent query down below here. So now you can actually reference it by its name that you defined up here, and as soon as this whole big select is done, that inline view goes away. It's a temporary view that you can utilize in your syntax of your query, but it's not persistent and it doesn't stick around as metadata. And this is going to be a new feature in MySQL 8.0. It's already in the developer milestone release of 8.0.1. You can play with it, and that's what I've done. The special case of the recursive query, it uses this interesting syntax where the query defined in your inline view has a base case and then a recursive step. Just like when we used to do proofs for recursion back in computer science classes, we'd have a base case and then a recursive step. I view it as very similar logic in that case. So you define an initial step that sort of seeds the initial row of data that should belong in your view, and then you say union all, or just union, and subsequently a query that references the name of the view itself. So there's the recursive step, that it actually references the definition that you're creating as part of the implementation of it. Kind of takes a little bit of mental leap to understand how this works. But let's see another example. A really good example that people struggle with MySQL frequently is generating a series of numbers. If you just want to have a set of numbers that you then are going to eventually join to other data, so you make sure to include all the rows in case there's no matching data, you can use this way to generate a list of those numbers. And here's my recursive step. I have my base case where I start out with the number 1, and I give it the name of the column that matches my definition. And then my recursive step is I am going to reference the name of my CTE here, my series, And whatever is the most recent row, I add 1 to it and return that as a new row for the view. And then there's a termination condition where it will stop doing this, so it will return 0 rows from this recursive step and stop appending to the view when I reach the limit of how I want to get here. If you, just like in other forms of recursion, if you don't give it a termination condition, it keeps on doing recursion until it fills up memory. So please be careful. Wear your gloves. Put on your hard hat. Another example is generating a series of dates. You may have data in your database that you want to report on, say, how many widgets did we sell on every day of the month, but I want to have the report include every day of the month, even if we sold 0 widgets. Well, now we can generate easily a list of all of the dates that are between some range, and then do a join to our sales data and get that out there. So this solves some of the problems that people have been struggling with MySQL for a long time. Before this, people would have to programmatically create a temporary table and fill it with values and then use that to join to your sales data. And it was a little bit of a tricky problem. Now, with recursive CTEs, you can do this on the fly, and the list of numbers will be cleaned up and go away automatically. You don't have to remember to drop your temporary table. How do we apply this to our tree of comments? Well, we could tell it to, our first scenario was query the ancestors of comment number 7. And in this case, we would say we start at comment number 7. We no longer have our closure table, so we're going to query the parent ID directly from our comments, just like the traditional adjacency list. And I say, I want my comment ID and the parent ID and other fields from that comment, and we start out with the base case of 0 as the depth. And then we union with the recursive step. The reading through the comments, we join our CTE comment tree, which we defined up here, to the new row from the comments, looking for the parent being of the CTE being the one we're currently searching for. So this builds up 1 row at a time all of the ancestors of comment number 7. It starts at comment number 7 and goes up the tree. And so there's where they relate. I did look at the visual optimization in MySQL Workbench to see how this is working, and it does a nice unique key lookup when it's adding to the rows as it's going through the recursion. But in the meantime, it's doing a full table scan of the view that it's creating. It's actually materializing a temp table of the data that it's collecting so far. And eventually, it produces something that it can union together. Interestingly, I was talking to Oystein about this, and I found out that the cost that it's reporting in this explain, the cost of the query is actually being reported assuming that it's only going to do 1 level of recursion. But of course, this is probably not the case. So the cost is maybe a little bit underrepresented. The other scenario that I showed for the other methods of doing recursive queries was to query a subtree. And here I would do it the other way around. I'd start at my comment ID number 4, and I go down the tree. And the condition here is the opposite. I'm looking for the nodes that are below the ones that I've already added to the CTE, and I keep on recursing until that doesn't find any. So, pros and cons. This is actually now standard SQL, conformant with the Ansi spec, which means it's also conformant with other vendors of SQL. So now you can write portable SQL code which will work on any vendor, and I showed you the list of all the other major SQL vendors that support this syntax. Now we can write code that is going to work across all of those. It works with the adjacency list, so now we don't have to do this denormalized fashion of storing the data and storing materialized paths or materialized lists of IDs. There's no more chances for anomalies to occur. There's only one reference from a given child to its parent. Cons. It's not compatible with earlier MySQL versions. Just like any other feature that is introduced in a new version of a product, if you're still using the old version of the product, or at least if you have a mixed environment where you have to keep supporting the old version of the product, it constrains you from using the new features for a while until we decide, okay, now maybe it's going to be 5 or 10 years from now, but finally someday in the future we'll say we no longer need to support MySQL 5.7. We can now only use features that are supported with 8 and newer, and won't that be a nice day when that comes? The other issue is that the use of materialized temporary tables has a chance of causing performance problems, and I found some mixed results on that. I'll do a little bit more demo in a moment. I also found this nice summary by user Marcus Wynand, who has a site modernsql.com, and he does very thorough analysis of different databases and how well they conform with standard semantics. And he shared this on Twitter, and I asked him politely, and he allowed me to use it in my slideshow if I give a reference to his site. But he wanted to make sure that this is based on the preview of 8.01 development milestone release. It's not GA yet, so we are not certain what's going to be in the final product. So take that as a grain of salt. But what my takeaway is from these graphs is that he identified a whole lot of different syntax and semantics features that he was looking for compliance with the standard recursive query feature and then compared them to different brands of other databases. And he found in all of his cases that MySQL passed with a green check mark. It's got this nice green column all the way down, and he points out that no other implementation of SQL is as strongly compliant with the standard. So woo, good job, MySQL people. This is maybe a long time coming, but worth the wait, and it's a great implementation of it in terms of standards compliance. So, and I wanted to test this out with a bit more large data set to try to see how does it perform at scale. How does it deal with larger hierarchies than just my 7-node comment thread. So I was looking around and I found a sample data set of the Integrated Taxonomic Information System, itis.gov. And they have a database of taxonomy information for biologists with every species known to man. They have over 544,954 nodes in one big hierarchy. And it's actually got 6 different root nodes, so it's not one hierarchy, I'm lying. But it's got plants and fungus and animals and bacteria, and those are like the root level kingdoms of this zoology data. When you download it, it's free, it's totally free. You download it and it comes in a zip file, and it's actually already prepped as an SQL script for MySQL, and you can insert that. The data that they provide to you, here's an example of an entry for the California poppy, the state flower of California, which is I can never pronounce this, Eschscholtzia californica. And they provide it in the taxonomic serial number, the TSN, which makes reference to its parent TSN in the data that they provide. That's 11 levels deep in the hierarchy. And it also comes with the path enumeration syntax of the list of all of its ancestors. Basically, its own breadcrumbs is provided in the data that they provide. So it's got both the adjacency list format and the path enumeration format in the database that they have. And I tried to experiment with this to write a little loop to take that information and then create a closure table out of it as well. And added an index to the table which they didn't have, just to have a compound index over the TSN and its parent. So the breadcrumbs query looks like this. You find all the ancestors for the California poppy, and you start with this base case, and then recurse up the taxonomy. My taxonomy is the name of my CTE, and you keep on going up, and then you can say, I want the taxonomy, and join that to the long names, the textual long names, to get that back. And it looks like that. So I've got my TSN, my parent TSN, my depth, which is actually reverse order. Notice since I started with the California poppy at the bottom and did the recursion all the way up, the depth actually goes up to the top of the plant kingdom to get to the top there. But what's the takeaway on this slide? Bingo, 0.00 seconds. It got that query, once I created the right index, it got that query in less than 1/100th of a second on a 500,000 row database. Not bad. When I did an explain on this, I noticed a few things. There's a new keyword that appears in the explain plan called recursive. That is a hint to us that it's using a particular implementation that is not something we had seen before in an explain plan. I also noticed that I have my covering index, so it says using index for both the base case and the recursive case. So that was a very advantageous index to create. I do have a file sort because I'm sorting by the depth of the report. If I don't care about the sorting, I can eliminate the file sort. What's missing here? Using temporary. I was expecting there to be a temporary table, because how could it be creating a materialized view without using a temporary? Well, it doesn't report it in the explain, but if you actually use the sys schema and start inspecting that, you do see some evidence of it. There's a report that says, this is literally the view in the sys schema for statements with temp tables. By definition, this statement had incurred a temp table during its execution, and it did one temp table for its recursive query. And you see a little bit more evidence of that when you use the sys schema to get the user summary by stages. You can see the point at which it cleans up the temp table and spends a little bit of time eliminating that. Question?
Explain bug then?
Could be an explain bug, although we've seen other cases where explain does not report that a query used a temporary table, particularly for those implicit temp tables that are created as part of other semantics, like derived tables and things. So maybe it's an omission, not a bug. The other type of query that I wanted to do was what I called the tree expansion. And let me demonstrate what I mean by that. This is a little demo app that I put together in Python to do what I call tree expansion. If I am navigating through a hierarchy of categories and subcategories, I would like to be able to click on one and have it expand and show me as I'm going down, and with successive indentation levels, and also show me all the siblings at that level as I go down. So let me show you what I mean. So I've cheated. I've color highlighted the right genus and families and kingdoms that I need to get down to my California poppy. So I'm going to click on this. Bingo, bingo, bingo. There's no caching going on here. This is actually doing live queries against the 500,000 row tables. And we're almost there. Eschscholzia, ta-da, California poppy and poppy yellow. And there's actually one more level deep because there's a couple of subspecies. So that is the closure table. That's the implementation that I showed you where we store every single path in the table, which has quite a lot of rows in it for a 500,000 row hierarchy. The CTE demo, I've got a slightly different query. It actually shows me all the root level kingdoms as well. And I can say, bingo, and I'll have to announce when I click, because click, click, a little bit slower, click, click, click. That's a little over 1 second for each of these to refresh. And click, and click, And there we go. So, what do we see in this? Here's the query I had to run, the recursive query that was able to produce that. Let me explain a little bit. I can go back to my full screen here. So I have a recursive query here that finds the ancestors. This is the breadcrumbs, where starting from a given node in the tree, so here's the one that I'm looking for, the child leaf node in the tree, I can then use that as my base case and go back up the tree through recursion. But the problem with that is the one we saw before is that when you start at the bottom and go up, then your depth is reported as maximum when you reach the top of the kingdom. And I want to go the other way because I want to be able to indent starting from 0 at the top level and indent down to the lowest species. So I actually need to go up the tree and then have another recursive query that's doing breadcrumbs to go from the top of the tree back down the tree in a different recursive step to get it in the right sequence of adding 1 to the depth every time I go back down the tree. So first I have this recursive query at the top that starts at a leaf and goes up to the plante, and then the second recursive query starts from that one and goes back down the tree the other direction so that I can get the correct notation for all the depths. Question?
Might it work to put this in a subquery and put an order by hand, or flip the order?
The question is, would you put it in a subquery and flip the order descending, but you still wouldn't have the correct values for the depth? Because, but how would you know what to subtract from? Because you don't know how deep you are in the tree. You have to start from the top in order to make that one be 0 and then count down. And then in addition to that, down after I finish defining those two recursive queries, so I've got my second recursive query making reference to the first recursive CTE in its execution. And then subsequently, once I have those defined, now I have a union down here because I want to get not only the up the tree and down the tree, but then I also want to get all the uncles and aunts. I want to get the other nodes at the same level so that are immediate children of each of the ancestors, which is pretty complex. But it was an actual real-world use case. You can imagine this type of a query being required for an application where you want to navigate through a hierarchy like this and expand out all of the siblings at each level as you go down. So here's the explain. Lots and lots of terms in the explain. A couple of things stand out to me. It's doing scans of a couple of times of the entire 500,000 row data set, doing all queries or index scans, so either one or the other or both. Here's an index scan, here's an all index scan. It's also got a using join buffer block nested loop. Sorry that went off the slide, but it's on there. So that's a pretty inefficient way of doing the join. I ran out of time. I apologize that I didn't have time to investigate this further to see if any indexes could have helped this. But given what I saw before with simpler recursive queries, I think there may not be ways to index every case. You may have to do table scans of the CTE as it's joining to other additional rows. So I need more investigation is needed on this. When I use the sys schema to look for statements with temp tables, I noticed this one created 3 temp tables, noted here. The total time for the query was 1.24 seconds, which is fairly expensive. User summary by stages sys schema table shows me that the majority of my time is spent sending data, which is another way of saying copying rows from one layer of MySQL to another one in memory, sending data from the storage engine to the SQL layer, typically. And that's the majority of the time. So that's what I found out from that. In spite of that, I mean, the test I ran was an outlier. It was a very large data set and a very complex query. It completed it in slightly more than 1 second, and that was on my poor little laptop. It wasn't on a real server. So I'm not really holding it against that. It actually succeeded in doing the semantics correctly, and I was able to do that. There's going to be exotic cases that are beyond the capability of any optimizer or the ability to scale. One of the lessons there is if you need to optimize for a particular workload, then maybe denormalization is the way to go. And I count the closure table design as an example of denormalization. So overall, I'm excited to see this in MySQL. I really congratulate the folks who implemented it. They worked very, very hard on it, and it works correctly. I'm very impressed. And the next step is, now that we have this feature, this capability in MySQL 8, when are we going to see it in applications? When are we going to see it in frameworks? When are we going to see it in ORMs? And that's not something that is up to the team at MySQL. It's going to be something that the whole community, all of us, need to start thinking about. How can we then leverage this new capability in our coding practices? So that's my presentation, and I can talk about it and take questions if you wish. Rick?
Try MariaDB 10.2.
Did I try MariaDB? No, I did not. I don't use MariaDB. Any other questions about this? Does this look like something that could potentially be useful to you in your development? There.
The wonderful book SQL Anti-Patterns. Where can we learn more about CTEs?
There is a few blog posts on the site for the developer blog for MySQL, where they introduced this feature when it was just in the labs. And if you just Google for MySQL recursive CTE, you'll no doubt find those as I'm sorry I didn't include them in the slide. And the manual, it has a number of good examples in the MySQL manual, which has a extensive manual page about the with clause with examples of both non-recursive and recursive CTE usage. And I'm sure we'll start seeing more blogs about it as we get closer to the GA release of MySQL 8.0. Yeah?
I use show status like handler percent to get better insight into what's going on in the.
Okay, so your comment is that another way to measure what's going on under the hood is to use show global state, show session status, to like handler percent, so you see exactly how many row requests are being run in the course of that. That's a great idea. I think that there are facilities in the performance schema that can also do the similar thing and in a non-blocking fashion. So. Great points. I'll repeat that for the recording. The performance schema has the stats broken down further, so you can get the stats per index instead of aggregated just at the row level, and that can give you some extra insight into how the internal I/O is being performed. Thanks, Oysten. Oh, interesting. So the performance schema does not report on temporary tables, and that's going to be a big factor in the recursive CTEs because they're preparing temporary tables. Interesting. All right. Well, thanks very much for everybody. If there's no more questions, I will thank you very much for attending and enjoy the rest of the conference.